I'm sorry, we are doing the risk center, so this should not be it. We found out the risk, so this should be OC. We are finding everything from OC. So this will be OC of 1 times okay. So that will take the square root. Or you can also write the square like this. If you want to write it like this, instead of multiplying it twice, you can always do it like this. It makes no difference. Okay, let's look at the output. So here you have the angle D and D3. Okay, so we finished the risk center. Now we need to do, what is step 4? What is the next step? Find R03. Exactly. So we need to find R03. Step 4 is find R03. Find R03 using T1, comma D2, comma D3.
First, one do the semicolon and one.
Okay, so if you, I'll give you an example here. Okay, let me answer that question for a second. The question is, when do I close with a semicolon, when I don't? So let's say, let me clear the screen. If I have something like this, let's say I want to do square root like this, right? If I don't close it with a semicolon, home, right? If I have it like this, it will print the output. Okay? If I close it with a semicolon, the output is suppressed. I don't see anything. So if I want to suppress the output, I don't want to print the output of every single line, I'll just use the semicolon to suppress the output. Okay? The reason I put a semicolon is because the output of that line is really not important. I don't want to see it, so that's fine. If you want to check every step that you have done, it's good to leave it without a semicolon. Okay, so let's do this. How do we find R03? How do we find R03? So the way to find R03 is basically to do this. The only way we can find R03 is to find T03, which is A1, A2, A3. We'll get a T03 matrix like this, which will be R03. Here we'll have OC 0, 1. This is a 4x4 matrix. Okay? Or in other words, this will be equal to, you will have R03, 0, 0, 0. Here you will have OC of X, OC of Y, OC of Z, and 1. This is your R03. This is what we need to extract from here. Okay? So what we'll do is we'll set up A1, A2, A3. So A1 will be equal to A1 will be equal to, the name of the manipulator is cylindrical, we wrote it as CYN. So we'll write this as CYN dot links dot 1. That means it's the first link. Okay, dot A, the A matrix for the first link times T1, theta. Okay. This will give you A1. Okay, let's run this one time, look at the A matrix, and then we'll come back. Okay, so this will be your A matrix. Go back. Do A2 and A3.
Is there a way that you can control the number of significant figures?
Yes, it's called precision. You can reduce it or you can increase it, but that's not really important because you're taking inputs. Huh? Okay, let's do the second one. That will be A2 will be equal to second link A matrix of D2. Okay? What is the A matrix? A matrix is the matrix that you do to find the forward kinematics. Right? I gave you a 4x4 matrix in a handout, AI. Sin theta, cos alpha, cos theta, sin alpha. Right? For each thing you have an A matrix. Each link has an A matrix, right? So if you have T03, this is for the first link transformation, second link transformation, third link transformation. Okay? Let's do A3. Okay, so now you'll have all three, A1, A2, A3. Let's run this. You should see the three matrices. One thing that you can observe here is because the last two links are prismatic, there is no change in rotation. You have identity matrices here. The only thing is the change in position because you have D2 is that this is D3. Okay? Now let's multiply all the three and to convert that into a T06 matrix, T03 will be A1, okay. So now what we'll do is we'll convert this into this matrix. I just need to check the command here. Give me 1 second.
Yeah, where?
Okay, so transformation to a rotation matrix is T to R. So what I'm going to do is I'm going to say R03 is equal to okay, what do we do next? So next is find R46 because we need to find the thetas, right? So here, we have this as, we know that R06 is equal to R03 times R36. So we need to find R36. The only way we can do that is we'll do this as R36 is equal to R03 transpose times R06. Set this up.
This is step 5.
Yeah, step 5. Step 5 is, let me write it here. Step 5, find R36. Set this equation up. So this will be equal to okay, R03 apostrophe will give you the transpose, okay, times R06. Okay, once we find R36, what do we find next? Find the last four thetas. So this will be find theta 4, theta 5 and theta 6 from R36. Okay, find theta 4, theta 5 and theta 6 from R36. So we'll do an inverse Euler. So inverse Euler will be equal to, this will have, I'm going to call it as let's call this as angles, right? Or let's call this as some variable which is intermediate, right? I'm just going to call it as temporary. Temp will be equal to TR to Euler angles. We are trying to get the Euler angles. You can get RPY also if you want RPY angles, TR to Euler angles, and we'll give the matrix R36. Okay, I'm going to comment here. I'm going to say use, okay, use TR to RPY for RPY angles. Okay, you can use this function to get roll pitch and yaw if you don't want Euler angles. Okay.
But the Euler is easier, right?
It's current frame reference. If you want fixed frame reference, it's RPY. Okay, let's run this and see the angles here. So these are the angles. Now you see that this is in radians. Okay, these are not in degrees, these are in radians. So let's convert this into a complete matrix, which will be your joint angle matrix. Your joint angle matrix should be like this. Q should be equal to theta 1, D2, D3, theta 4, theta 5 and theta 6. The angles, let's set them up in degrees. The length is obviously in whatever units the system works in, so let's not worry about that. The angles will set it back to degrees. So we'll say here, I'm going to say Q, the joint vector, step 7 is set up the joint angle, or let me write it as joint displacement vector. Q. So Q will be equal to, the first one was T1 times, I'm going to say 180 by pi because I'll convert it into degrees. Okay, that is the first one. 180 by pi will give you. Then we have D2. Then we have D3. Okay. 4, 5, 6 is in here, is in temp. So what I'll do is I'll say temp times 180 by pi. Okay. So this should give you all the 6 joint displacements. When you go here, you'll see everything angles in degrees. Okay, Q, and these are the angles. Let me write it here. I'm going to say angles in degrees.
But I got this answer for the Q, for the TMPs.
Okay. Now let's say that I give you a different structure. So what changes in this program if I give you a different structure instead of a cylindrical manipulator? If I ask you to code a inverse kinematics program using decoupling, what would change here?
L1 to L6.
First thing is your DH table would change. Second thing that would change, DH table is simple. The second thing that would change is the inverse kinematic solution. Okay? Because if the structure is different, the first three joints I have given you this, but in your case you will have to derive the first three joint angles. Okay? So for example, theta 1, D2 and D3 is computed based on geometry of the structure, right? So if I give you a different one, it could not be an RPP, it could be an RRP, right? So it will be T1, T2 and D3. Or it could be all three angles, so it will be T1, T2 and T3, okay? So I want you to do this. Go ahead and change the position and orientation to these values, and then again find the orientation.
Say again, Professor.
I want you to change the P, the position is now this,
Okay.
the orientation is this. I want you to find the inverse kinematic. So change the vector there, and actually let me do one thing here quickly, just give me 1 second. Give me 1 second. Okay, just set that up here and we can.
So the position is the same.
We are the same.
We did the same one?
Yeah, they are the same one.
Oh, okay. All right. It's exactly the same. Actually, I solved this for you. All right. Let's find. I thought it was different in the. Okay. Anyways. Okay. Let's do this. I want you to, because we did this, go back and we changed the toolbox. Try to run the previous code because you had an issue with the workspace. Remember? Plotting the workspace. It works now,
Yeah.
right? So just try that. Try the previous example where we had plotting the workspace. Actually, we can plot this manipulator also. So now here, you can go here and say, let me go to the window here. This already has prismatic lengths, but we have not defined the limit of the prismatic lengths. So let's go here and you can define the link here. So these two are prismatic joints. So before that, what I can do is I can say L2 dot QLim is equal to 0 to 3, let's say. And then L3 dot QLim, because these two are prismatic joints, will be 0 and 4. Or let's keep it as 3. Okay. Alright, so now what I can do is, once I have the joint limits, I need to define a workspace also. So let's try to do this here. Plot CYN, comma, Q. If I do this, it should give me an error saying workspace is not defined. Okay. So let's set up the workspace, and I'll say here. So you'll be able to see the manipulator structure here.
Can we see the editor?
Huh?
Can you see the editor window? The
Editor window?
With L2, Q link, L2.
Okay.
Thanks.
For a few minutes.
Check this.
Show us the plotting command, please.
Absolutely. So if you want to do teach, you just go here. Okay, cyn.teach, and it will add. So now you can move any joint you want. Okay, you can change you can lower D2, you can lower D3, or however you can change the orientation. Okay, you're still in the new toolbox. You're in 10, you're not. You're in 10. Just type in VTR. Dot teach with the parenthesis. So you just type in this one, cyn.teach. Here when I see this one, see Okay, you don't have the joint, where is fuel limit? So first plot it, plot the plot command and then do the thing. Run the plot like that. Okay, it's already there. Okay, you are in the wrong toolbox, you have to change your toolbox. Oh, Victor, okay.